The overall goal of this procedure is to generate higher-order Laguerre-Gauss optical beams at high purity for use in high-precision interferometry. This is accomplished by first designing and prototyping the optimal phase conversion pattern to convert a fundamental mode optical beam into a desired higher-order Laguerre-Gauss mode using a spatial light modulator mode converter, and then manufacturing a phase plate converter based on the prototyping results. The second step is to inject a fundamental mode laser beam onto the manufactured faceplate to produce a Laguerre-Gauss beam at low purity. The produced beam is carefully profiled, matched to desired new beam parameters by means of lenses to be eventually injected into the linear mode cleaner cavity. Next, the linear mode cleaner cavity operates as a mode selector to the injected beam. Locking the linear mode cleaner allows separating the desired Laguerre-Gauss mode from the residual unwanted modes, rejecting these, and eventually increasing the overall mode purity of the generated beam. The final step is to design the mirrors required for the desired performance of the Laguerre-Gauss mode in a full-scale detector. This is achieved by simulating subsystems of the detector and reducing certain shapes in the mirror surfaces until the desired performance is achieved. Ultimately, analysis of the intensity profile of the generated beam is used to assess its purity.
The main advantage of this technique over existing methods is it allows for generating of a stable, high-purity beam. This also allows for a high degree of adaptability within the experimental setup.
Though this method can provide improvements in performing high-precision interferometric measurements, it can also be applied to other areas of science, such as materials processing, microscopy, motion sensors.